In the last class we discussed about AGC and AVC and also started mentioning the fact that the same system can be utilized in amplitude stabilization of oscillators. We have shown how that can be indicated by adjusting the loop gain to be exactly equal to 1 when the phase shift is the required value 0. Now, a problem illustrates how this can be achieved in a Wien bridge oscillator for oscillating at a frequency of 1 kilohertz with a peak voltage of the sinusoid at 10 volts. So, the basic configuration, let us draw. Wien bridge oscillator uses an RC network for fixing up the frequency RC, and that is used in the feedback path, and we have to have a gain fixed at 3, and that is, let us say, being done by a multiplier put in the feedback path. So, the beta of the network is determined by the multiplier as in fact, if this is V naught, this is going to be V naught into Vc by 10. So, the gain of this is going to depend upon the beta factor, which is Vc by 10, and therefore, since the gain of this amplifier is 1 over beta, okay, the gain of the amplifier is 10 by Vc. This should be exactly equal to 3 for the amplitude to be stabilized at exactly equal to 10 volts. So, at 10 volts the gain should be 3 or Vc should be equal to 10 by 3 or 3.33 so on volts. But prior to that, most probably it was not oscillating when it was switched on, it should build up. That means the gain should be greater than gain of the amplifier. So, this should be greater than this 3.33, that is, the gain should be greater than 3. Okay. Let us say, therefore, Vc should be less than 3.33 volts. Gain should be greater than 3, and therefore, Vc should be less than 3.33 volts. So, let us say it should start at 3 volts or so. We can now put our AGC, AVC system here such that to start with this voltage is somewhere around 3 or so, let us say, and then it goes on to 3.33. So, we can have an arrangement where Vc starts with, let us say, 3, Vc initial is 3 and Vc final is 3.33, let us say. So, we must have an arrangement like that. This is necessary for us to start the oscillation. So, let us therefore put our usual AGC scheme where we have put a precision rectifier. So, it will rectify the half wave here. So, we get negative going half wave here. Okay. If this is, let us say, R dash, this should be R dash. So, if this is a sinusoid like this with peak like this, Vp naught, this will be the negative half wave going like this minus VOP here, okay. And then we put the low pass filter, which is now converted into an integrator. We have seen this, the Miller effect and all comes into picture, R double dash, and we will put a voltage reference here. Since this is negative, it will give you a negative average, voltage reference should be positive. So, at the time of starting, this has no voltage here, amplitude has not built up. So, there is V reference which is positive, this will be driven to negative saturation. Let us say the supply voltage is plus 15, minus 15 for this op amp. So, it will go to minus 15 volts here. So, this minus 15 volts has to be converted into something suitable, so that Vc becomes equal to your 3 volts, so that it can start oscillating. So, we will put an attenuator here. So, we will connect here plus 15 volts, okay, let us say. So, this voltage becomes 3 volts initially, that means this is alpha R, this 1 minus alpha times R, an attenuator. Okay. So, the voltage here is minus 15 into alpha plus 1 minus alpha into 15, minus 15 into alpha comes here. Due to this plus 15, we have 1 minus alpha times that. That should be equal to 3 volts. So, which is nothing but 1 minus 2 alpha into 15 is equal to 3 volts, okay, or 1 minus 2 alpha is 3 by 15, okay. So, which is 1 by 5. So, 2 alpha is equal to 1 minus 1 by 5, which is 4 by 5. And therefore, alpha is equal to 4 by 10, which is 0.4. So, if alpha is 0.4, the voltage here is going to be at 3 volts. Now, what happens? The amplitude starts building here from 0. This negative voltage keeps increasing, and this negative voltage keeps increasing means it is applied to minus. So, this will become more positive. So, from 3 volts it will keep increasing. Okay. So, it becomes more positive. Okay. So, it might become 3.1, amplitude is still increasing, 3.2, 3. Ultimately, it will go to 3.33, at which point once when this becomes 3.33 automatically, right, what happens is the gain is exactly equal to 3 for this stage. Further amplitude build up will not occur, because now the amplitude is going to be such that V reference is going to be equal to V p naught by pi for this kind of relationship. And therefore, if we want output voltage peak amplitude of 10 volts, that divided by pi should be the voltage reference that you have to connect here, 10 by pi here. This is one answer. What is that equal to? So, about 3.18 volt. So, if you apply that voltage here, then the amplitude is automatically going to be adjusted to exactly 10 volts peak. Now, only one thing is left out, the frequency f naught is equal to 1 by 2 pi R C, that is required to be 1 kilohertz. So, 10 to power 3, okay, hertz. So, R C is going to be equal to 1 over 2 pi into 10 to power 3. Let us select R as 10 K. So, C is going to be, let R be equal to 10 K, then C is equal to 2 pi into 10 to power 4 into 10 to power 3, which is equal to, okay, this is nanofarads, let us say 100 by 2 pi nanofarads, which is equal to 15.9 nanofarad. Is that correct? So, we will now discuss what is called as voltage controlled oscillator. This is an important circuit which is basically used for FM generation. we had seen earlier how multiplier can be used for AM generation, for example. In fact, the circuit that we have just now discussed in earlier example itself can be used for AM generation, because we know that we are able to build a sort of an oscillator to oscillate at a certain frequency. In that example, it was 1 kilohertz. Let us suppose that is the carrier frequency, and you want to modulate the amplitude of the carrier. So, you simply vary the V reference based on the modulating frequency. So, now you will get at the output an amplitude modulated sort of carrier at 1 kilohertz. So, this is very easy to generate AM using such amplitude stabilized oscillator. So, you just simply vary the V reference by a modulating frequency. Automatically you will have an amplitude which is controlled by the modulating frequency. So, it will become an AM. If you want an FM to be generated, on the other hand, you have to have control over frequency, and this can be done by using the following circuits. We had earlier discussed circuits which can generate voltage controlled oscillators by using multiplier. You can actually use double integrator loop, oscillator, quadrature oscillator, and replace each integrator with multiplier integrator combination and obtain a voltage controlled oscillator. For example, if an integrator is being used, RC, and I put a multiplier along with it, this is VC, this is VI, this is V naught. We know that V naught over VI is equal to minus VC by 10 SCR. This we had earlier itself indicated when we discussed filters and all that. Suppose therefore, we use another integrator like this and give it to the same VC and put this integrator in the loop, right. So, we give the feedback now. This ideally speaking should go into oscillation, because minus Vc by 10 SCR, if you start from here, so that into Vi, and that again squared, if you further integrate, and then with a negative sign minus 1 inverter, is going to be equal to Vi. So, this into Vi is equal to Vi. This can happen only at a certain frequency, because omega C R squared will give you this with a negative sign, because S squared is going to be j omega C R squared. So, j squared is minus 1, that gets cancelled. So, that happens at omega naught equal to 1 over C R into Vc by 10. So, if you build an oscillator like this, it is a voltage controlled oscillator. It is linearly proportional to the control voltage. The frequency is linearly proportional to the control voltage. Only thing is, this may not oscillate because of the non-ideality of the op amp. So, what it means is, there is certain amount of let us say negative feedback here, which might have to be countered by a positive feedback from this side. So, you might have to give a positive feedback in order to make this go into oscillation, right. And you can bring about again the amplitude stabilization loop, such that the positive feedback is there only when the amplitude is 0, and the positive feedback gets compensated by the negative feedback exactly at the required amplitude. All that can be done by using again a multiplier from here, can put a multiplier here, okay, and then so this gives you negative feedback here, this one, this has given you fixed positive feedback. So that initially this positive feedback only dominates, there is no negative feedback here. So the control voltage is 0, that means this output is 0 and only positive feedback exists, and then this output builds up, VC becomes positive and some portion of this is fed back here, so that the negative feedback comes into picture. So this is a voltage controlled oscillator with amplitude stabilization scheme possible. How do you stabilize amplitude? Once in this particular circuit, if this is Vp sin omega t, this output is going to be Vp cos omega t, because this is integrator, right. And if this is Vp sin omega t, this is going to be Vp cos omega t, and therefore we can square these using multipliers and simply add. Therefore, the way to build this circuit is you just take these outputs, square these, and add. Adding can be done by using just a resistive network like this. If this is done, this is Vp sin omega t, this is Vp cos omega t. So, what we will be getting here will be Vp squared by 10 divided by half because of this resistive attenuator, okay, into sin squared omega t plus cos squared omega t, which is 1. So, you get a DC voltage which is Vp squared by 20 here straight away without really using any rectifier. This is the uniqueness of this circuit. Okay. This is why it is called quadrature oscillator. These two outputs are at quadrature, that is a phase shift of 90 degrees. So, that can be exploited in getting an amplitude, okay, which is a DC dependent upon the amplitude Vp squared by 20, and this can be therefore compared by means of this comparator, okay, and we can actually V reference we can put, and this can be used to control the you can see so many multipliers being freely used. These two multipliers are used in order to make the frequency become directly proportional to the control voltage. This, let us say Vc dash, is primarily for amplitude control. So, this is something that will control the amplitude. Amplitude therefore, is going to be V reference when that becomes equal to Vp squared divided by 20, right. So, Vp is 20 into V reference under the root. So, you can see that in order to build a good voltage controlled oscillator using this circuit, I have to use two multipliers in order to make it a linear voltage controlled oscillator, and then must also stabilize the amplitude. This circuit therefore, is not very popular. Only thing is it gives you a sine wave with linear voltage dependence of frequency. You just now saw the complexity of the linear voltage controlled oscillator if that has to be a sine wave, because it has to have a voltage amplitude stabilization scheme and the voltage frequency should be directly proportional to voltage. Normally, the VCOs that are abundantly used are not sinusoidal. The reason being that it is pretty complicated to get VCOs which have stable amplitude and linear frequency control. What is done is you use an integrator along with a Schmidt trigger. This we had already discussed we discussed a stable multivibrator, use of Schmidt trigger in generating waveforms. So, what we can do is put an integrator and then let this integrator have a multiplier, so that the time constant of the integrator is again controlled by the multiplier. So, this is R, this is C. So, if this is V I, this is going to be V I, okay, by R 10 R C, okay, into V C with a negative sign into integration. Okay. So, what it really does is that it will do integration, okay, dt. So, this is equal to minus V C by 10 R C into integral V I dt. So, now we will do the time domain analysis rather than Laplace, because this is going to be connected to a Schmidt trigger, okay, which is going to be a regenerative negative feedback circuit that we have discussed earlier. Let us say this is now plus positive feedback, local positive feedback is there, and therefore, this is R, this is let us say R, and then this is now connected to the input. Let us see what happens. So, because there is regenerative positive feedback here, output has got to be either at plus V supply. Let us say this is plus V supply and this is minus V supply. It is either plus V supply or minus V supply. It cannot be at any intermediate point, okay, because of the regenerative positive feedback. This is the Schmidt trigger. So, if this is at Vs, this voltage is Vs. So, this particular thing is a constant voltage Vs. So, it will integrate that. So, this is Vs. So, it will be coming out of it and this will be simply T. That means, this will be directly proportional to time, the voltage will be decreasing. So, if this is Vs, let us plot that. Let us call this V naught 1, then this is V naught 2, this is V naught 1, and V naught 2 is going to be decreasing like this linearly. What will be the rate at which it is decreasing? It will be minus V C by 10 R C, okay, minus V C by 10 R C into T, right. This is the way it is going to decrease. So, this is going on decreasing, this voltage is plus Vs. As soon as this reaches minus Vs, this voltage is going to become 0. That is the state in which this Schmidt trigger is going to change state from minus to plus. So, it will go to minus, okay, plus to minus here. So, this has gone to minus, okay. So, this will go from plus to minus at that point. So, this as soon as it reaches minus Vs, okay, this particular thing will change state from plus Vs, okay, to minus Vs. Okay. So, this has gone to minus Vs. The moment this goes to minus Vs, this is minus Vs now. So, the slope here will become for this waveform plus, and it will be plus V C by 10 R C into T. So, it will go on like this. This is already at minus Vs. So, this is going on increasing. The moment this voltage becomes plus Vs, this voltage will become 0. It will again change from, okay, minus to plus. So, this will keep happening, okay, forever. So, the moment this gives this thing, it will go to plus Vs and this will go down. Right. So, this will be kept at that until this goes to minus, okay, again it changes state. So, you get triangular waveform here at this point and square waveform here. The time period can be easily computed. This is T by 2 because this whole thing is T. So, T by 2 into V c by 10 R c, this is the rate at which it goes, V c by 10 R c, okay, into T by 2, it acquires a voltage of twice V s. There is minus V s to plus V s it goes, right. So, V c this V c is going to be there, right. This particular thing into V s, right. This particular thing into V s, yeah. Please remember that this particular thing into V s is all the time there, right, because this is V s constant. So, this V s gets cancelled with this V s. So, T is equal to 40 R c, right, or F naught is equal to 1 over T, okay, this 40 R c by V c, okay. 1 over T is V c by 40 R c. So, this particular thing is a nice voltage controlled oscillator, linear, but it uses only one multiplier. It does not require any amplitude stabilization scheme because already the amplitude gets neatly stabilized at plus V s and minus V s, and this rate of rise and rate of fall become same, equal to minus V c V s by 10 R c and plus V c V s by 10 R c, okay, respectively. And therefore, this is a very popular circuit for generating FM, as I told you, and because you give the modulating frequency here, so automatically you can now have the carrier getting modulated by this particular frequency here, voltage here, okay, and this frequency will start changing according to this control signal, right, linearly. So, this circuit can be also converted into its transistor counterpart, okay, wherein this portion is going to be replaced by a voltage controlled integrator. That means, you will have a voltage controlled current source driving a capacitor, that is all, okay, and a transistorized mid trigger. But the basic circuit is essentially this, okay, and it is this VCO which is very popular, and this entire circuit is normally called a function generation circuit because it is giving you a square wave, a triangular wave, and also if you just put a function generator, in the sense diode function generator, to convert this triangular waveform into sine wave, that we had done long ago in the first part of our lectures. You can convert this sine wave, triangular wave into sine wave, you get all the three important waveforms, sine, square and triangle, with voltage control of frequency, okay. This chip is available as a function generator IC chip. Now, we will consider an important control loop which is called phase lock loop, or PLL it is called. This has become very popular because of the fact that such a phase lock loop is available as an integrated circuit, and it can achieve a large number of communication as well as control systems like speed control, frequency synthesis, FM detection, AM detection, etc. Therefore, let us see the basic principle of what is called phase lock loop. Before we go to phase lock loop, I would like you to understand the basic principle of negative feedback as taught to you in control system. If Xi is the input and Xf is the feedback factor coming from the output, which is X naught, this is called error detector. In control systems, this is called error detector. This will give you an output which is Xi, this is put here plus minus, saying that it will give Xi minus Xf as the error, and this is called the error amplifier. Therefore, X naught is going to be equal to the gain G times Xi minus the feedback factor Xf. This is how you have been writing your control loop equations, where X is any variable. So, this particular feedback factor, if it is H, this is the way the signal gets transmitted, output is fed back to the input. So, Xf is equal to X naught into H, then this is equal to G into Xi minus X naught into H. So, now from that we get X naught by Xi is equal to G divided by 1 plus Gh. This is an important control system equation which tells us that if Gh is, this is called loop gain in our controls or circuits, we have been calling this as loop gain. This particular loop gain, in this case it is negative feedback, actually therefore the loop gain, if you really consider the loop, is negative. So, this is a negative feedback configuration. If this loop gain is much greater than 1, right, then we can show that this is approximately equal to 1 over H. It becomes independent of G, the amplifier. It becomes only dependent upon the feedback factor H. And if H is 1, this is equal to 1. That means X naught will follow Xi. X naught is going to be following Xi. This particular thing, if Xi is voltage, you can call this V naught is going to follow Vi. Vi is going to an error amplifier, which is nothing but a differential amplifier. So, plus minus. So, this entire thing is nothing but a differential amplifier. This error detector with G, and if I give feedback fully, V naught follows Vi. This is therefore called a voltage follower. This we have discussed again in the first part of our series of lectures, voltage follower. Again, if I say this is II and this is I naught and this is a current amplifier, this also we have done in what we call as a transistor connected as a diode. This error detector in fact can be very easily done by just merging this into a node, because then this particular thing is going to be, in fact, if the direction is changed, it will just give you I minus I naught as the error output. So, if you change the direction of the current here, the error detector becomes just a node. This is a current amplifier, and therefore, I naught is going to be very nearly equal to II, is therefore called a current follower. So, that in fact is nothing but a current amplifier like common emitter amplifier. When entire collector current is fed back to the input, okay, it becomes a common base amplifier and the current gain becomes very nearly equal to unity. So, you have understood long ago that I can design such control system equivalents in circuits by using voltage as the parameter, current as the parameter, etc. Now, when we go to phase lock loop, neither voltage or current is going to be the considered input here. What is going to be considered input here is nothing but phase, and this is going to be, right. Let us say we will put this whole thing H equal to 1. Okay. This is not going to be error detector, it will be called, okay, this is phi I and phi naught. This is going to be therefore called phase detector. That means, a phase detector is something that when phase is given as the input, phase difference is given as the input, it will give you a DC output corresponding to the phase difference. This DC output is amplified, okay, and this output of the amplifier has to be converted again into phase. So, what is that converts a DC voltage into phase? That is nothing but, okay, a VCO. How? Because when I apply a voltage, DC voltage here, you get a frequency. What is the relationship between frequency and phase? I know that if phase is phi, the frequency f is nothing but d phi by dt. Frequency and phase, they are linearly related. So, frequency phi f, okay, or actually speaking this is equal to omega in radians per second. It is nothing but d phi by, this is radian frequency, is nothing but d phi by dt, rate of change of phase. If you now put Laplace transform, omega is equal to s times phi, or omega by s is equal to phi. So, if I have frequency, I can say that if the frequency output is given to a phase detector, it will respond to phase change. And therefore, the basic building blocks of a phase lock loop will be a phase detector, a VCO, and an amplifier, and it should respond to only average here because DC I said. So, amplifier with a low pass filter. So, let us now list out the basic building block: phase detector, amplifier plus low pass filter, then 3 voltage controlled oscillator. In fact, we had discussed all these 3 building blocks just earlier. Voltage controlled oscillator has just been discussed. Amplifier and low pass filters were also earlier discussed, how to design amplifiers and how to design low pass filters. Phase detector was discussed when we discussed multipliers. So, all these basic building blocks of the phase lock loop have been earlier discussed. Their characteristic we have obtained. What is the phase detector characteristic? It will give you an average output corresponding to some let us say kPd to phi I minus phi naught. This particular kPd is called the phase detector sensitivity. amplifier sensitivity is called gain. So, amplifier gain is called A naught DC gain. Low pass filter has a cutoff frequency. So, that low pass filter characteristic will be looking like this 1 by 1 plus S by omega low pass, first order low pass. This also we have discussed earlier. That is omega LP is the cutoff frequency of the low pass filter. Voltage control filter, voltage controlled oscillator also has a sensitivity. What is it? Frequency omega is dependent upon control voltage. If it is linear, okay, it will be directly proportional to the control voltage. So, this is called KVCO, this VCO sensitivity. Omega is equal to KVCO times VC. So, the basic parameters associated with these building blocks will be phase detector. If it is linear phase detector, it has a sensitivity factor, amplifier gain A naught, low pass filter cutoff frequency omega LP, voltage controlled oscillator has its sensitivity factor KVCO. So, if we now try to analyze this for the phase, what will we get? If phi I changes and phi naught will follow it, phi I by phi naught should be equal to 1, because that is what we have been all throughout telling. It is immaterial what the variables are. In this case, phi I by phi naught by phi I, or phi naught by phi I in fact is equal to 1. So, we can call this as a phase follower, or as it is popularly called, we can call it as phase locked loop. The phase follower action is going to be considered as phase locked loop. So, what it means is d phi by d phi naught by d phi, change in phase is going to be followed at the output if there is a change in phase at the input. We have just now seen how the phase lock loop comprises of 3 basic building blocks: a phase detector whose phase sensitivity is KPD, an amplifier with low pass filter, it is necessary, so that the output of the phase detector, which is really, this is actually a multiplier. So, it will comprise of both high frequency and low frequency component. It is the low frequency component, the average component to which output should respond. So, we have put an amplifier with low pass filter here, and then this DC or the low frequency input is controlling the VCO frequency. So, output is going to be a frequency, but just now I said the phase and frequency, they are related. Omega is d phi by dt, change of phase. That means, when I am using phase here in the analysis, this frequency omega should be converted into phase. That is done by dividing by S, because this omega is equal to phi into S, Laplace transform. Differentiation means multiplication by S. So, phi is equal to omega by S. So, KVCO by S is the transfer function of the VCO here, which will indicate that it is the phase that is of interest for the phase detector. That is the case now, we can do the analysis. Assumption is that only the phase is varying. Let us now see how this is going to respond. Phi I minus phi naught is the phase difference, and KPD into that is the DC voltage here, or low frequency voltage here, and that is getting amplified by A naught divided by 1 plus S by omega LP. that is the DC voltage appearing here, and KVCO by S is the phase conversion factor here. So, KVCO by S, and that should be equal to phi naught itself, right. So, this is exactly similar to our writing x naught is equal to xi minus x naught into G. This whole thing is going to be called as the gain or the loop gain. So, we will call this G into phi I minus phi naught. So, what do we get? We get phi naught by phi I equal to G by 1 plus G. If this loop gain is very high, this is going to be very nearly equal to 1. So, that is why we call this a phase follower. Phi naught is going to be followed, change in phase at the input is going to be followed at the output. Now, what is G? The loop gain here is nothing but KPD KVCO into A naught. So, that divided by S into 1 plus S by omega L. This factor, which is independent of frequency, is called the DC loop gain of the this KL, which is nothing but you go through this KPD A naught KVCO, all the sensitivity factor products, you call this as DC loop gain. So, this is going to be equal to KL divided by S into 1 plus S by omega. If you write, therefore, this equals 1 by 1 plus 1 over G, this is going to be 1 by 1 plus G is okay, here 1 over G S by KL plus S squared by KL into omega L. This is going to be equal to phi naught over phi I. If all these factors can be ignored, if KL is very large, this is going to be equal to 1. So, but we have also shown that omega naught, okay, here phi into S is equal to omega. So, omega naught into S is equal to phi naught, omega I into S is equal to phi I. So, this gets cancelled. So, if it becomes a phase follower, it will also have frequency following action. Output frequency is going to be same as input frequency. This is an important property of phase lock loop. Output frequency will be exactly equal to input frequency.